Efficiency of heat pumps powered by natural gas power plants. Background: many buildings and homes in climates similar to Urbana-Champaign use a natural gas burning furnace for heating during the winter season. However, electric-powered air source heat pumps have become somewhat more common in recent years due to advances in technology causing increased efficiency. While these heat pumps can get electricity from any source, currently natural gas plants generate the largest part of it. And our objectives were to determine whether it is more efficient to use natural gas for furnace heating or to generate electricity to power heat pumps, to demonstrate that heat pumps are adequate for colder climates such as Urbana-Champaign, and to demonstrate problems with the models and trade-offs of using heat pumps.
The natural gas power plant model is a combination of a Brayton cycle with exhaust heat heating water into steam for a steam cycle, as seen in Figure 1. For the Brayton cycle, we modeled the combustion as a heat input into an air standard analysis, with air considered as an ideal gas. In the analysis, kinetic and potential energy effects are neglected, and all processes are assumed to be well insulated. The compressor and gas turbine are assumed to be isentropic. An isentropic efficiency of 0.8 was used for the steam turbine and pump. With reasonable estimates for temperature and pressure values, we calculated a thermal efficiency of 0.6289 for the combined system. Assuming 80% of the possible energy from the natural gas entered in process 2-3 as heat energy, this means that 50.31% of the possible energy from the natural gas is converted into electricity.
A vapor compression heat pump model was used in Figure 2. The model was designed to be similar to the real air source heat pump in the Linux heat pump, of course. Refrigerant 410A is used as a working fluid. Kinetic and potential energy were neglected, and saturated vapor enters the compressor and saturated liquids exit the condenser. The model presumed at a 22 Celsius interior temperature and was modeled at several exterior temperatures. There are two models, one with 65% isotropic compressor efficiency and one with 75%. The model COP results are compared with the COP data from the Linux heat pump in Figure 3. Both models are slightly more efficient than the real heat pump due to simplifications and assumptions of the models. This is also true for the power plant model.
As you can see on Figure 4, even for very low temperatures, the power plant and the heat pump model produces more heating from the same amount of natural gas that a furnace would. The heat pump can also be powered with any electricity source, not just natural gas power plants. However, the cost to heat ratio with a natural gas furnace is only 4.78 cents per kilowatt hour, about half of the 9.75 cents per kilowatt hour cost of electricity in Illinois. Our conclusion is that while the models used are slightly optimistic, the general trend seen will still be true. A combination of a natural gas power plant with an electrical heat pump will be a more efficient use of natural gas than a furnace for nearly all exterior temperatures. Adoption of heat pumps is slow right now due to switching costs and the higher price of electricity, but they have several advantages which will encourage more use in the coming years.